Thomas, thank you very much. So I only have a little bit of antiferromagnetic there, but I think we will do more antiferromagnetic wires soon because I work on the theory with Andrei Bernovic, because the way we do it is like we follow theory prediction. This is a nice thing with the topology part. Topology, first I define the topology, because now people claim, like Andrei, Ashwin, and all their co-workers, I belong to also one group, that we have characterized now all the materials in the inorganic database, whether they are topological or not. But since this all is based on a single particle picture, it's very limited, and so far we didn't do magnetic wires, and we didn't do antiferromagnetic wires. Okay, so we do mainly single crystal growth. And then the next step, and this you will learn to identify whether you really have this topological material. You look for the surface state, because it looks like that the topological materials all have very characteristic surface state. So this is based on DFT. Then you compare the DFT calculated surface states, like here in the example, with the Inge resolved photo emission, which is more or less a photograph of the surface state. And then we are very much interested if these topological materials have additional properties like superconductivity, and people, for example, think that in molybdenum telluride there's unconventional superconductors, so which means it's maybe a potential material for Majorana fermions and topological quantum computing. And so we are looking not only for the topological superconductors, TSC means topological superconductors, we are looking also for quantum anomalous Hall effect at room temperature, because if you want to make a topological quantum computer device for Majorana, it would be good to have very stable quantum anomalous Hall effect at higher temperature, or topological and topological superconductor. So, but what you are interested in is in magnetic materials, so we're doing now high throughput calculation on ferromagnets, and you will learn today that it's very easy to find ferromagnetic wire semimetals, but everybody knows also that the antiferromagnets have the trouble of correlation often, so you cannot go with a single particle picture, and people like Andrea are working on this, but it's very challenging to find this. So these are what theory has to do now to really work on the new concept for magnetic topological materials. So what we are doing, I said already, we are growing single crystals, but we are also doing thin film growth, and I think co-workers of us will talk about some results in thin films and in antiferromagnets and antiferromagnetic materials. But I focus on the magnetic materials. The thin film were grown here in our thin film lab. Okay, so I want to talk about ferromagnetic wire semimetals, which means I talk about wire semimetals where we break time reversal symmetry. So, and wire semimetals, you know, are related to these crossing points in the electronic structure, and these crossing points are coming in pairs in case of wire semimetals, and I want to explain you that they are quite common in ferromagnets. So we all know, so for topological materials, we are looking for bands which are crossing. And in topological insulators, it's very often an S band, which is a conduction band, and a P band, which is a valence band. And S and P band, as valence and conduction band, appear very often in semiconductors. So if you have this crossing area here, because it's not a line, what can happen, depending from the symmetry of your crystal, we can have a forbidden crossing here, so we can open up the forbidden crossing area, and we end up with a topological insulator which has a gap and between the conduction and the valence band, and there's a part of the valence band in the conduction band and vice versa, and this is very often symbolized by Möbius stripe. So then you get an insulating crystal which has a very nice surface state which looks like the Dirac cone of graphene and has also very interesting spin structure. So depending on the symmetry of the crystal, what can also happen that you can have points in the Bryan zone which are protected, for example, by, in case of Dirac, or white semimetal, depending from the symmetry elements, very often these are mirror planes. And then it's not allowed to open up the crossing in certain points, which means you end up with a band structure, which we know from graphene, with crossing points. And depending from the symmetry of my crystal structure, they can be Y points or Dirac points. So Dirac points are easy to identify because they are at high symmetry points. So the crystal structure should be much of higher symmetry. So then you have these Dirac points, which you find simply if you draw these bands along certain high symmetry lines, what we commonly do in DFT, so you can find them. Y points are appearing in crystals which have lower symmetry, and at lower symmetry points, therefore, they are very often hidden somewhere in the Brillouin zone, and we don't know. There's a relation between the Dirac points and the Y points, so I can transfer a Dirac point by breaking the symmetry into a Y point. So the Dirac point is a 4 times degenerated point, and then I can split them into the Y points. And the Y points, therefore, are even super interesting because they have chirality. So I have a kind of magnetic monopoles if I split these Dirac points into Y points. The nice thing and the good news is here again, Dirac crossing, split it into Y points. The nice and good news is every crossing, Dirac crossing, or every crossing in a ferromagnet are Y points. So I'm surprised that not more people look for Y points because there must be many. Everybody knows how many crossings you have in a band structure. So all the spaghettis which you have and they are crossing, they should be wide. So therefore, I only talk about examples, and I think you should find more. Okay, so therefore it's very easy to find it more or less everywhere, and you can imagine I'm looking with my special glasses. I see everything in the family of Heusler compounds, and indeed we looked for all these topological properties also in Heusler compounds. This is one of our business. Okay, so and the nice thing I already mentioned that we can have topological insulators in the binary semiconductor like mercury telluride, and we can have topological insulators in the ternary semiconductors. This is the 111 Heusler compounds. This is easy to understand because you more or less can get the same electronic structure with 2 elements as you can have with 3 elements. We only have more possibility to play. And these compounds are, despite of being topological insulators with band inversion, they are also non-conventional superconductors. Anyway, so today I talk a little bit more about this Heusler compound because they have 2 magnetic sublattices, and this makes the whole story much more interesting. So in this family, we can find also semiconductors which are related to the conventional semiconductors like gallium arsenide. We can find a lithium-2, manganese, magnesium, I have to count electron, tin compound. But we also can find unusual semiconductors in this family of materials like iron-2, vanadium, aluminum. It's a non-magnetic semiconductor despite of having 50% iron. So the electronic structure has 24 valence electrons here. So we have not only the sp orbitals occupied, we have also some of the d orbitals occupied. But if we think in spin direction, we have 12 electrons in one spin direction and 12 electrons in the other spin direction. And this is a symbolic band structure of iron-2, vanadium, aluminum. So, or you can write it in the language of LIGO. So this is one iron, this is the second iron, this is the aluminum, and this is the vanadium. And they all together have 12 electrons in each spin direction, and we have a non-magnetic material. So if we apply more electrons than the 24 electrons, so we can have half-metallic ferromagnets, and this is not new for the audience from Kaiserslautern and Mainz, because they're working on Heusler compounds since a long time, from the time I was still in Mainz. So you can have a compound like cobalt-2 manganese gallium. This has 9 electrons from the cobalt 2 times. Manganese has 7 valence electrons, gallium 3. So in total, we have 28 valence electrons. And in the case of a half-metallic ferromagnet, there are 12 electrons in one spin direction, 12 for the core states here in this direction, or the anyway, the same states here. And then the additional 4 electrons, they go only in one spin direction, which leads to a density of states, which has a gap in one spin direction and no gap in the others. So then we only have to deal with one spin states, and this is already an advantage. So there's a big family of cobalt-2 Heusler compounds, which are half-metallic ferromagnets. So you simply count for different composition the number of total electrons. This is 25. Then we know we have to measure 1 mu Bohr as a magnetic saturation moment, because we have 24 plus 1, 28 is 24 plus 4, and 30 is, for example, 24 plus 6. So you see this also in the language of LIGO. So, or you can make a graph, like here's a magnetic moment which you measure, and this is the number of valence electrons, and you see, as expected, most of them are lying on a line. Since you also increase the spin, the exchange splitting by putting more and more electron in one spin direction, you increase also the exchange splitting, and you see that with this in a Meer field theory, or even also in reality, with increasing number of electrons, we also increase Tc of this material. And if I have the goal to make quantum anomalous Hall effect at room temperature, I should look in Heusler's, because I easily find Heusler compound with a Tc higher than room temperature. So the first theoretical prediction of magnetic ferromagnets in Heusler's came from Andre Bernewig, and it came from Princeton at the same time, then also from Heusler. You see, here's the total band structure, fully relativistic, calculated for cobalt-2, titanium, germanium. We already for cobalt, titanium, tin, they are the same silicon. So they have 2 mu Bohr, and if you do it fully relativistic, you have not a good spin is not a good quantum number, but you nicely see that in the gap there's this nice crossing point. They are slightly above the Fermi energy. The 0 here is the Fermi energy. So these are candidate materials for this crossing point. So you simply have to look now through all the magnetic materials in every database, and if you find crossing points, you will see you can write very nice papers in very nice journals. So it's not really a difficult change. Okay, anyway, so we looked for something else. When we saw this publication from Andre, we immediately recognized, oh, we already had white semimetals in Heusler compounds, because long time ago here in Mainz, I worked with people who are now members of the Claudia group, and so we looked for a Hall, the anomalous Hall effect in Heusler compounds, and we found a giant anomalous Hall effect in cobalt-2, manganese, gallium, aluminium. And at this time, slightly later, so Jürgen Küppler did calculation based on the Berry phase, and we found a very nice agreement in this compound between the measured Hall effect and the calculated Hall effect. And the reason for this is here also because we have this Y crossing around the Fermi energy. At this time, we simply did a calculation, and therefore Heusler, Weyl, and Berry. So you know Heusler, Weyl, the crossing. So the anomalous Hall effect is a function of the Berry curvature. And this was a little bit contradicting what people did in Spintronics for a long time. They always had the assumption that the anomalous Hall resistance scales with magnetization. And now you can imagine if you simply look for the number of valence electron, and here you see the anomalous Hall effect, it should go linear like Tc and everything. But it is not the case, because it goes really with the Berry curvature. So it looks like that the Heuslers are really nice systems where the Berry curvature counts more than extrinsic effects. Okay, so then now recently in 2016 we have revisited cobalt-2, manganese, gallium, and aluminium, and we have nicely could see that we have nice Y points in these compounds, so which are related to the large anomalous Hall effect in this compound. So in this sense, we can already say that the topological properties can maybe be useful for more than quantum computing. So they maybe can be useful for spintronics and for maybe even energy conversion, because what we learned here in a toy model, so that if we have crossing points in the band structure, so we can conclude that we have a large Berry curvature, and we have a large anomalous Hall conductivity and a large anomalous Nernst conductivity. So nowadays we do always Hall measurement and Nernst measurement from these materials. And even we have large magneto-optical responses if we have this large Berry curvature. So even in some classical properties, we see unusual properties in this compound. In cobalt-2, manganese, gallium, we already measured the Hall effect, so this was nothing to do. But we could go back and remeasure the Nernst effect. And indeed, in this compound, we found a giant Nernst effect. Here is a Nernst measurement, and they look very similar from the behavior, like the anomalous Hall measurement, and you see large values. And if you then see here the Nernst effect as a function of temperature, you see it increases, and it will increase up to Tc, so it's even higher compared to what we could measure in our equipment, because we only can measure up to 400 Kelvin. So if you compare then the Nernst effect as a function of magnetic moments for different compounds with cobalt to manganese gallium, you see that there's a big effect. It's 1 order of magnitude larger than what you know from other magnetic materials. So you see really the strong enhancement based on the Berry phase. And you should remember, we will talk later about manganese-3 tin, and people here on the conference will talk about manganese-3 tin, which shows also a large enhanced Nernst effect. So it seems to be that in the Heusler compounds, you see they have many mirror planes, which is good for having crossing points instead of gaps. And we have nodal lines in this compound, and if we apply a magnetic field in a certain direction, these nodal lines turn into Y points, and we have many Y points. Don't ask me, I never counted, people ask me always, but it depends on the magnetic field. And you see here in this cobalt to manganese gallium, you see really here this soft magnetic behavior, but a giant anomalous Hall effect. And if you calculate the Hall angle in this compound, it's already larger than 10%, which means the quantized Hall effect would be 100%. So we are not, you see that this compound is not so far away from being at the quantum Hall effect. So you must make thin films and out of plane magnetization eventually. Okay, so for the Spintronic community, because I always was asked, why do we ignore the extrinsic part? So we are really lying here with cobalt to manganese gallium, and later you will hear about cobalt tin to sulfur 2, which is also magnetic white, nicely in this intrinsic Berry phase regime. This is, I have to put the reference here, sorry, after this Alan McDonald, Gyrosinova, and so on, paper, the review about the anomalous Hall effect. Okay, good. With Heusler together, we could even show the nodal line. If we have, if we measure this compound, it's a soft magnetic material, we cannot see the Y points, but we can see the nodal line in cobalt to manganese gallium. There's a nice agreement between the calculated and the measured band structure. And the prediction was that there are drumhead surface states. So surface state seems to be one must for most of the topological material, and this is indeed what you see. You see the predicted surface states also in nice agreement with the calculated surface states. You can, as I said, so for certain electron counts, we really can find the 26, which was predicted by Andre, and the 28, some very nice anomalous Hall effect and very nice crossing points in the band structure. But there are other compounds, the inverse Heusler compounds, which are spin-Gapler semiconductors, and in the next point we investigated the relation between them. So we can make compounds with the same electron count like in the full Heusler structure, but we can do this also in the inverse Heusler structure. And the interesting fact is that we have inversion symmetry here and no inversion symmetry there. So it's a nice toy model, the Heuslers, to play with topology and to distinguish between donuts and Berliner. So unfortunately, we have no donuts. Oh, we have kind of donuts there, so you can play the game later in the coffee break. So we know that cobalt to manganese gallium has this very nice mirror plane and this large anomalous Hall effect. And here you see the Berry curvature in reciprocal space. You see, because of the high symmetry, the Berry curvature has to have nearly everywhere the same sign, and therefore we have a large Berry curvature. So this, what I talk about here, about the anomalous Hall effect, is also valid for the spin Hall effect, because also the spin Hall effect is strongly increased in materials which have many mirror planes, because the spin Hall effect is based also on the Berry curvature and the anomalous Nernst effect, etc. pp. So there are properties of the Berry curvature. But what we do, if we remove this mirror plane and make, for example, with the same compounds on the same number of valence electrons, we can do it. So we remove this mirror plane here. You see here we have inversion symmetry mirror plane. Here we have no mirror plane. So we immediately allow the barrier curvature to be still large, but having different signs in the Brillouin zone, and this leads that they cancel out. And interestingly, we can make high magnetic moment in this compound without a anomalous Hall effect. So the anomalous Hall effect disappears. And it would be nice if you could show this in copper manganese arsenic, transfer Weyl points into a non-Weyl point compound, because you could even imagine you remove a mirror plane by changing the spin orientation. So what is the band structure background here? So here you see, for example, the band structure of cobalt titanium tin, which has the same number of electrons as this compound manganese cobalt aluminium. And you see here we have crossing points in the band structure because these are Weyl points, they are forbidden crossing. But here we remove a mirror plane, and this crossing point become forbidden crossing, and it open up a band gap. And this is now why this compound is a so-called spin gapless semiconductor or magnetic semiconductor. So we always were wondering why there are so many spin gapless semiconductor or semiconductor, magnetic semiconductor with high TCs in Heusler compounds, and now we understand. So they are the counterparts of the Weyl points or Weyl semimetals in the Heusler family. So because if you remove one mirror plane, you open up a band gap instead. So you turn a donut into a Berliner by simply changing, removing one mirror plane in the Heusler compound. So now you can do all this high throughput and do all the calculation for all the known magnetic Heusler compounds, and we focus mainly on the Heusler compound. And what you see in general, this is the Hall conductivity and the Nernst effect. You see the effect is much larger for the space group 222, which has a mirror plane, compared to the space group 216, which has no mirror plane because of symmetry reasons. You could do, and we did the same for the spin Hall effect for the people who do real spintronics, and so on. Then it's the same. So 225 is much better than 216 space group. Okay, so then you can think, and this is what we did also for spintronics, we can even distort the compound to have a crystalline anisotropy and to have a magnetocrystalline anisotropy, and we can do this in the 1, 0, 0 direction or the 1, 1, 1 direction. So then we can have a hexagonal version or a tetragonal version, and very often if you go to the manganese-rich Heusler compounds, you have a phase diagram which has all the 3 phases. So it depends from if you grow thin films or so, you can grow cubic, hexagonal or tetragonal Heusler compounds, and some of them even have a temperature-dependent phase transition, like the magnetocaloric compound. They go between these 2 structures. The tetragonal structure can be even more complex, what we know from magnetocalorics. There are many different superstructures here. However, the hexagonal compounds are very interesting, and you will hear about this family of compounds, the manganese-3 germanium, because they have a Kagome lattice, and therefore they are the antiferromagnetic Heusler compound. They are frustrated, so we calculated even 2 years before this paper all the potential magnetic structures of this compound. And we found that we have in this non-collinear antiferromagnets an anomalous Hall effect, which was surprising, especially for Stuart. He was originally co-author. He removed his name. But at the same time, Alan MacDonald found in another Kagome lattice in manganese-3 iridium a similar spin structure and also a large anomalous Hall effect. So this was the reason why we published the paper. And later it was clear that these compounds have Weyl points, the spikes in the Berry phase at the Fermi energy. And I still think this is strongly connected and should be also the case here. I think we have some evidence because this compound is also topological. This we know from recent calculation. Okay, so this doesn't show the anomalous Hall effect as predicted, but it might be a domain problem in this compound. This compound shows this, and you will hear more from Nakazuchi. I think about this work. You see that this has a very nice large anomalous Hall effect in manganese-3 tin, and we did the manganese-3 germanium, which shows very nice large anomalous Hall effect in this compound. And you see here is a typical Heusler compound, which is antiferromagnetic. So if you calculate here the Berry phase, you see here is the spin polarized density of states. The red for one spin, the blue for the other spin, and the green is the Berry phase, and it's interesting. The Berry phase is 0 all over the energy range, so you will see there are different cases. If you have, for example, a compensated ferromagnet, this is different. It's only 0 at the compensation point, but here it's 0 everywhere. So it's really amazing that in these non-collinear structures, you have a Berry phase. And I'm sure there are also many, many more examples in oxides, etc. Okay, this compound has also, as expected, the large Berry phase. Here's again the work of Nakazuchi and of Kamara and Benyan. They see also a very large jump in the Berry phase. And again, this graph, if you compare it to all the other magnetic compound as a function of the magnetic moment, so manganese 3 tin has a very, very tiny non-compensated moment. You see it's much larger than expected. It's not larger than the other compounds, but it's already larger for the small magnetic moment. But this Kagome lattice in tin compounds is not a very rare case, so you can mix them with manganese, with iron, and with cobalt. And the MIT is heavily working on this, so they have several high-impact papers on the iron compound. So they found a massive Dirac fermion in the iron 3 tin to iron 3 tin 2. But as you can see, there are all kinds of composition in which this family, these materials occur, and the magnetic substrate layers are more or less separated by space, even depending from the composition. So for example, iron tin has even a larger separation. And people who are in theory, they like Kagome lattice because this is a toy model band structure. So despite of having crossing points in the band structure, you have also flat bands, and the theory is super excited about the flat bands. And now people try to put the flat bands even at the Fermi energy, because you have a flat band here which comes only from the symmetry. And all these flat bands in the Kagome lattice are topological, so they expect that they see some new interesting properties. So we looked after manganese. On the cobalt compound, there's a compound cobalt 3 tin 2 sulfide 2, and I have to say it was inspired in some sense by Dima, because Dima came to me and said, can you mix this compound? We want to find skyrmions. I'm not sure whether he found skyrmions so far, but when we made the compound, we recognized that the band structure, so this is the crystal structure again, so these are the cobalt layers, and here we are at, there's a small area where there is a Ney phase, but normally it's out of plane magnetized. This compound's below 100 K. So this looked for us very interesting, and what we always do is doing a DFT calculation, and this is a DFT calculation. And everybody in the room now recognizes there are Y points close to the Fermi energy, because this can be even recognized by somebody who has no idea about physics, because simply every crossing point in this ferromagnet is a Y. So this is a crossing point. So they are very close to the Fermi energy. So again, if you have no magnetic field, so there is a nodal line. So if we apply magnetic field, this material is even hard magnetic. We see we have Y points in the Bryanson. So we expect very large Fermi arcs, much larger than we know from the non-magnetic system. And the nice thing is the Y points are close to the Fermi energy. So our first work was on transport properties, and one thing we proved, and you have to believe me, that there's a chiral anomaly, which people believe that this is a signature of the wild fermions in the transport behavior. Anyway, so it's not as impressive as in the non-magnetic material, but we have now even much nicer data. But the next step is then up. So this is a theoretical prediction of the Fermi arcs in this material, and this was investigated by Julian Chen's group. And these are the experimental observation, and it's quite clear that the experiment and the calculation are in nice agreement. And you have to look here very careful on the termination, because the crystals are quite complex. So we have this honeycomb lattice of the cobalt, but we have also the possibility of tin and sulfide termination in this material. Anyway, so the Y points are indeed slightly above the Fermi energy. This is the uppers from the compound, from the virgin compound. But to see the Y points, we have to dose it a little bit with potassium, so we can move the Fermi energy close to the Y points, and you see nicely the Y crossing via this potassium dosing. So then in the transport properties here is the anomalous Hall conductivity. We see a nice plateau up to and large value up to Tc. And it, as I said, it shows a kind of hard magnetic behavior, so we have a nice hysteresis. And if we again see this in the context of extrinsic and intrinsic anomalous Hall effect and scattering, so we see it belongs again here, as you can see here, to the intrinsic phase, so the justification of the Berry phase is here fully valid, similar like in the Heusler compound. Here we have even an Hall angle of 20%, so we are even closer to our quantum anomalous Hall effect, but it's below room temperature, but people who are working in the fields know that the quantum anomalous Hall effect in the bismuth selenide doped semiconductors is around, I think, millikelvin high, and in twisted graphene they recently saw a quantum anomalous Hall effect at 7 Kelvin, and they are super excited. McDonald is super proud. And here we are working at other temperature. And you see again also that this compound doesn't show any trend, so it's based on the Berry curve, which shows a much larger effect. And then you can measure the Nernst effect, and again the Nernst effect is much larger in this compound than you would expect because of the Berry phase. It's again the same observation as in cobalt-2 manganese gallium and manganese tin. You see the strong enhancement of the Nernst effect. Here it's even larger, the ratio to the magnetization than any other compound. So thinking about the quantum anomalous Hall effect, so this is one of the holy grails in topology and devices of topology, but it could be also the holy grail for spintronics. So we know from the quantum Hall effect was discovered by Klaus von Klitzing. So in a high magnetic field at very low temperature, so you have this protected edge states for every spin direction, for example, in a 2-deck of gallium arsenide. So so Lorenz Molenkamp, he found it in mercury telluride that you don't need a large field, so you can have even the quantum Hall effect in 2-deck of mercury telluride because of spin-orbit coupling. You get the edge states, protected edge states, even without a field. And in graphene, we know the quantum Hall effect can be even reached at room temperature, so but still a field. And the quantum anomalous Hall effect in a magnetic material we want to have here, then you have only one spin polarized edge state, and this would be cool because people in spintronic, they dream always of a poor spin current. Anyway, so for cobalt-3 tin 2, so for 2 we did the toy model calculation. We said, look, if we have in the bulk the crossing point, what happens if we go to a monolayer? And indeed, the monolayer should be a quantum anomalous Hall effect. Then we did DFT calculation of a slab of cobalt-3 tin 2 sulfide 2, and we indeed find the edge states for this compound and the quantum anomalous Hall effect for this compound. But this is so far theory. But we have already experimental evidence, so we have some co-workers in SDM. So Vidya, she looked at the edges of some of the samples, and she nicely sees the quantization of the chiral edge states here on the cobalt edges, which has exactly the lambda levels you expect for the quantization. So the lambda level 1, 2, 3, 4. So we think this is already evidence that this might be a 3D or kind of 2-deck, many 2-deck 3D quantum anomalous Hall effect in this compound. So the quantum Hall effect in 3D was recently found in zirconium telluride, so we are looking forward to see quantum anomalous Hall effect 3D eventually in cobalt-3 tin 2 sulfide 2. Okay, so I hope I convinced you that with these magnetic vials, which are so easy to identify, you can do a lot. You can do even find interesting Nernst effect, interesting anomalous Hall effect, but also maybe have a recipe for going beyond to have maybe quantum anomalous Hall effect and a way to new devices in quantum computing. Thank you very much.